All right, so we're going to talk first of all, and this is just going to be a short intro video of what is calculus, why do we need it? So if everything could be left in algebra world or in geometry world, okay, that would be great, because then we wouldn't need calculus. But here's the issue. Let's look at a roller coaster, okay? So if we have a roller coaster, let's do the Texas Giant. And back in 2013, a lady was thrown and she was killed on the Texas Giant. So here's my little roller coaster. What they found out was that she was at an elevation of 75 feet when she was thrown. But it's not like anybody stopped and said, oh my, she was thrown at this particular point. We should take notes. You know, everybody was panicking. So how did they know that she was at a height of 75 feet from the ground when she was thrown? And what they did was they had to work backwards from where she landed and look at the velocity of the roller coaster and that type of thing in order to come to the conclusion of where she was and what happened. So what we're going to do is we're just going to leave this as, this is my little thing. So the words, goodness, the roller coaster comes around the track like this, yes? And then it goes up and then it goes down, okay? So what happens when you're right there on the roller coaster? You know, you're coasting around this way and then you start to go up a little bit. What happens right there? All of a sudden you get this, huh, right? And the car is grabbed by a chain that's underneath. And then what do you hear? You hear, and it's a regular, constant sound. So basically you are going up, and let's just say, I don't even know, I'm making this up. Let's just say you're going up this hill at 2 miles an hour, okay? So that's what the chain does. So a couple of words to recognize is constant, rate of change, okay, of change. And the word constant implies algebra. If you've got a constant rate of change, that's your slope. Okay, so don't think of this slope. Don't think of the hill. Think of how the car is moving. It is moving at the same speed here as it is here, as it is here, as it is here. So it is a constant rate of change in elevation. Now, what happens when we get to the top of the mountain or hill, whatever? At the top, what lets go? The chain lets go and it just circles back down and it goes in a loop, okay? So what takes over when you're at the top? When you're at the top, gravity will take over. So here's the question. How fast are you going here? Well, you're going pretty dang slow, okay? How fast are you going here? You're going faster. How fast are you going here? You're going real fast. How fast are you going here? You're going heck fast, okay? You're going heifer fast. So what happens is that gravity takes over. So on this side, you have algebra. It is a constant rate of change. Over here, you have calculus. And this is instantaneous rate of change. Because when you're this far into the fall, you're going slower than when you were this far into the fall. Okay, so it's not constant on this side. So when we talk about rates of change, constant is going to apply algebra, so is average. If we talk about average rate of change, that's also going to imply algebra. And you know that that formula is y2 minus y1 over x2 minus x1. That's your formula for slope. Okay, so when we get on this side, this is where calculus has to take over. Because I want to know how fast at a specific one singular moment in time that car is moving, or whatever other context we want to have. Okay, so this type of calculus is called differential calculus. So differential calculus is going to talk to you about rates of change. It's going to talk to you about velocity and acceleration. There's 20 million different ways to apply this stuff, but the broader example or the broader application is going to be instantaneous rate of change. That's what we're looking at. Okay, a couple more vocabulary words. We've got differential calculus, which means we're going to take derivatives, or what is the derivative, okay? We're going to differentiate. So differentiate is another word that's going to come up, okay? And then we have the differential, okay? So there's all these little words, but notice they all have differ in them, pretty much. So that's all going to be addressing rates of change, that type of mess. What we're going to do is in chapters 2 and 3, that's going to be learning about differential calculus. Okay, so what is this mess over here? If we're going to find area under the curve, so I'm just going to leave my little picture here because I'm running out of room. Let's pretend like I want to know the area underneath this hill, okay? So it's all fine and great and wonderful if I know a geometric formula, but I don't. So I know squares, I know circles, I know rhombuses, I know all this kind of mess, but I don't have a formula for this shape because it's kind of sort of parabolic, but not quite. Don't even know. All right, so basically, area under the curve is going to be integral calculus in its most basic form. Okay, so that's going to be starting in chapter 4 and 5, and then from then on. Okay. So what we do is we integrate, we take the integral, we have an integrand, we have all sorts of vocabulary words for that, and so we'll hit that in more detail in chapter 4. But your two basic types of calculus is differential calculus and integral calculus. And that's where we're going to go from here. And so section 1.1 is going to kind of sort of help you understand what both of those are. And then give you examples on how we can use algebra or geometry to approximate, since we don't know calculus yet. So that's where we're headed. So just know that, and then again, as we go through, like when we start chapter 4, I'll go through all of the vocab again. But I just wanted to give you a basic idea of why you're doing what you're doing. If life was just about algebra and straight lines, it would be great. If life was just about simple shapes that we know the formulas of, life would be great. But life isn't that clean. And so we end up with calculus. And that helps us with this stuff. Last thing is, I told you that this is chapters 4 and then on. So here's just a little side note. If I have this question, if I ask you, what is the answer to this? Well, hopefully you would say it was 12, okay? And we have different ways of approaching that. I could use multiplication. I could write 3, 4 times and add it together. But it's pretty straightforward. That is differential calculus. We show you the rules. You find the rule that fits the scenario or fits the context, and you apply that rule, okay? Well, now, here's the new question. Come over here. What if I tell you the answer is 24? Well, what was the question? The question is 3 times 8. Does that work? Sure it does. What about 2 times 12? Absolutely. What about 4 times 6? Yes. What about 1 times 24? Absolutely. What about 1/2 times 48? Okay, so this one opens up a whole can of worms because you're actually working backwards. And that's why integral calculus is so hard, because you may have a generic starting point and you just apply the algorithm and get your answer. But if I give you the answer, you have to work backwards. You've got to find the indicators and look at the context to find out how to work that out. So integral calculus is a whole lot more intense than differential calculus. And when you hear about differential equations, you're actually integrating, okay? Because you're undoing everything. But that's your basis. That's what we're headed on this thing. So that is the only intro video I think that I'm going to do. But just know, as far as concepts, okay, so boy howdy, I can't talk today. Just know that that's where we're headed. We're going to do differential calculus, we're going to do integral calculus, and then section 1.1, it's only 8 problems, but I did a lot of explaining on concepts, and so that's why there's 4 videos for it. All right, so go forth and do section 1.1. Hang on, I have to delete.